Hey guys, there are a few things that we didn't get to cover in class today, so I figured I'd go over them, just a few topics. We have symmetry, even and odd functions, intercepts, and logs. So I figured I'd make this quick video for you, and we can go from there. So we're looking at three different kinds of symmetry. Symmetry about the x-axis, about the y-axis, and about the origin. For symmetry about the x-axis, if you're given an xy point, say right here, you know that on that graph is also x negative y, which would be like right there. Right? So you check by inputting negative y into your function, and seeing if the function's still the same. All right, for symmetry about the y-axis, it's super similar. Graphically, this is what it looks like. So if xy is on the graph, we know that negative xy is also on the graph. In this case, you input negative x to see if function is the same. All right, so if xy is on the graph, negative xy is also on the graph. An example of that would be y equals x squared, or y equals the absolute value of x. Those are both symmetric about the y-axis. And then finally, symmetry about the origin. That's the case where if, change colors here, if negative x, or rather, if xy is on the graph, then negative x and negative y are also on the graph. All right, an example of that would be like x cubed, for instance. All right, so we call functions that are symmetric about the y-axis, we call these even. And functions that are symmetric about the origin, we call odd. And we talked about this yesterday when we said that cosine is an even function and sine is an odd function. All right, the next thing I want to talk about is intercepts. This is really simple. You guys probably remember this from algebra. I just want to review it real quickly. So to find the y-intercept, just plug in 0 for x and solve for y, right? To find the x-intercept, it's the other way around. Plug in 0 for y, solve for x, right? Because at the y-intercept, x is obviously equal to 0, and at the x-intercept, or intercepts, y is obviously equal to 0. All right, so it's that easy. All right, and the last thing I want to talk about are logs. Everybody's favorite topic. With logs, we have three particular properties that I want to remind you all of. The first is the product property. So if you have log base b of m plus log base b of n. Remember, they have to have the same bases. We can combine those and say that that's equal to log base b of m times n. And that's the product property. All right. The second property is the quotient property. And in this case, we have log base b of m minus log base b of n. And as the name implies, quotient, divide, we're taking our arguments and we're dividing those. So that's equal to log base b of m over n. And then last but not least is the power property. If you have a as your coefficient, log base b of m, that's going to be equal to log base b of m to the eighth power. The eighth power, not the eighth. All right, so make sure you write those properties down. I'll give you a second to view those. Feel free to pause your video. I'm going to erase now and show you a few more things about logs. All right, remember with logs, we can write them in log form or in exponential form. So you have log base b of a equals x. To change this to exponential form, remember, if you had me for algebra 2, I talked about this little like loop-de-loop method, where you start with the base, you take it to the answer, and that's equal to your argument. All right, so log base b of a equals x. That's the same as b to the x is equal to a. A few other things to remember. Log of 2, if there's no base written, we automatically assume that the base is 10. So in this case, this is the same as log base 10 of 2. Natural log of 2. Natural log, it just means that we have log base e of 2. You might be like, oh man, this e thing, what is that? If you remember, e is Euler's number. Euler was a mathematician in the 17th century, I want to say. Really interesting guy. He was actually blind and memorized entire volumes of math, so that he could do math into his later years whenever he was blind. He would just do everything from memory. Really fascinating guy, but I digress. E we use in compound interest formulas. It's going to come up a lot when we look at derivatives later in the year. You don't have to worry about that, but it is an important number that we're going to come back to. And if you remember, E is, I shouldn't say equal to, E is approximately 2.71828, and it's an irrational number like pi, so it does go on forever. All right, I'm going to end the video here. Make sure you watch this, and yeah, thanks for hanging with me. We'll come back to this tomorrow. I'll see you guys.